Isaac Newton was born in 1642 in Lincolnshire, England, the son of a farmer. Despite his humble beginnings, Newton would go on to become one of the most important figures in the history of science. As a child, Newton was considered to be quite introverted and had a love for learning. He was particularly interested in mathematics, which would become his lifelong passion. Despite his father's wishes for him to become a farmer, Newton's mother recognized his intellect and sent him to grammar school. In school, Newton excelled in his studies and was soon admitted to Cambridge University. It was here that he began to develop his theories on mathematics and physics, which would eventually lead to his groundbreaking work on calculus and the laws of motion. One of the most famous stories of Newton's early life is his encounter with an apple. As the story goes, Newton was sitting under an apple tree when an apple fell to the ground. This event sparked his curiosity and led him to begin thinking about the laws of gravity. This eventually led to his famous law of universal gravitation, which states that every object in the universe is attracted to every other object. Newton's work on mathematics and physics was not limited to just gravity. He also made important contributions to the field of optics and the study of light. His work on the nature of light and color laid the foundation for the development of the modern science of optics. In this video, we will discuss his development of calculus. We will begin with a brief summary of what exactly calculus is before moving on to its history. Calculus is a branch of mathematics that deals with the study of change and motion. It was independently developed by Sir Isaac Newton and German mathematician Gottfried Wilhelm Leibniz in the late 17th century. The two branches of calculus are differential calculus and integral calculus. Differential calculus is the study of how a function changes. It helps to determine the rate of change and slope of a curve. It is used to understand concepts such as velocity and acceleration in physics, and is also used in economics to study how a quantity changes with respect to another. Integral calculus, on the other hand, deals with the study of accumulation of quantities. It helps to find the total change in a quantity. In physics, it is used to study concepts such as displacement and area. In economics, it is used to study concepts such as cost and profit. Calculus is a fundamental tool in many areas of science and engineering, such as physics, engineering, economics, and computer science. It also plays an important role in the field of medicine, helping doctors to understand the rate at which a patient's condition is changing and to make more accurate predictions about the future. What many people may not know is that Newton's development of calculus was not a straightforward process. It was, in fact, a result of his attempt to resolve several mathematical paradoxes that had puzzled mathematicians for centuries. One of the most significant paradoxes that Newton encountered was the concept of infinitesimals. Mathematicians of the time had long struggled with the idea of infinitely small quantity, as they seemed to defy the laws of logic and reason. Newton, however, was not content to simply accept these paradoxes as unsolvable mysteries. He set out to find a way to make sense of these infinitesimals and use them to develop a new branch of mathematics. Another paradox related to Newton's development of calculus was finding a way to calculate the area under a curve. These were among the most significant paradoxes Newton attempted to succumb on his journey to developing calculus. Newton's willingness to confront these paradoxes head-on and his relentless pursuit of understanding led him to develop calculus. The concept of limits is essential to understanding both differential and integral calculus. In differential calculus, limits are used to understand the behavior of a function as it changes and to calculate its derivative, or the rate of change of the function. In integral calculus, limits are used to understand the behavior of a function as it accumulates and to calculate its definite integral, which gives the total change in the function over a certain interval. One of the key applications of limits in calculus is in understanding the behavior of functions at points where they may not be defined or may have infinite values. For example, the function 1 over x has an infinite value as x approaches 0, but by using limits, we can understand how the function behaves as x gets arbitrarily close to 0 without ever reaching it. Another application of limits is in optimization. By using limits, we can find the maximum or minimum values of a function, which can be used in a wide range of applications, from physics and engineering to economics and finance. In conclusion, limits play a central role in calculus and are an essential tool for understanding how functions change and accumulate. They They are used to make sense of the behavior of functions at points where they may not be defined or may have infinite values. Their applications are wide, from understanding the behavior of functions and optimization to physics, engineering, economics, and finance. Newton was able to use this concept to develop new techniques for measuring and analyzing the motion of objects. He also developed the concept of a derivative, which is a measure of the rate of change of a function. This allowed him to analyze the motion of objects and the forces that govern their motion in a much more precise and accurate way. In the middle of his life, Newton published his groundbreaking work, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, in 1687, which laid the foundation for modern physics and is considered one of the most important scientific texts of all time. The book included his laws of motion and law of universal gravitation, which explained the behavior of objects in motion and the forces that govern the motions of all objects in the universe. Despite the success of Philosophiae Naturalis Principia Mathematica, Newton was not content to rest on his laurels. He continued to work tirelessly on his research, and he made many other groundbreaking discoveries in mathematics and physics. For example, he developed the technique of fluxions, which is now known as calculus of Newton. He also made significant contributions to the field of optics and was able to explain the nature of light and color in a way that had never been done before. At the end of his life, Newton was celebrated as one of the greatest scientists of all time, and his contributions to mathematics and physics continue to shape the way we understand the world today. He is remembered as a brilliant mind and a true visionary whose work laid the foundation for many of the scientific and technological advancements of the modern world. His early struggles with the concept of infinity and other paradoxes led to the development of calculus, which is one of the most important tools for understanding the natural world. His works like Philosophiae Naturalis Principia Mathematica laid the foundation for modern physics and is considered one of the most important scientific texts of all time. Newton's contributions to science and mathematics continue to shape the way we understand the world today, and his legacy will always be remembered as one of the greatest scientists of all.